Okay, let's do this. Test, test, test. Test, test, test. Okay, I think it's working. Let's see. So yeah, we're back with another I guess episode. I'm Leetcoding until I'm a Leetcode god. I think it's part 12 right now. I haven't streamed it in a while, but I have been Leetcoding. I just honestly I wasn't really feeling like streaming, but I definitely need to get more consistent with it. Let me see. So you can see like the problems that I've done. I got through trees, and then I did like 2 try problems. And now I'm trying to get better with backtracking. Backtracking to me is so confusing. I don't really understand it. Like I'm going over the solution to subsets. I did this problem 2 days ago. And like I read a comment on YouTube. It was this the solution on Leetcode's YouTube channel, and the comment broke it down like very well. And I understand the process of like building the tree, of like basically all the decisions you can make, but the step of going from the tree to implementing it in code confuses me. So I don't really know, man. Let me. So yeah, I feel like a lot. I'm not gonna stream that long. I have other stuff I have to do. I'm probably only gonna stream like an hour, so I'll probably get off at like 3:40. But the majority of the stream is probably gonna be me like analyzing this question and making sure I genuinely understand the process. Cause like I could memorize the solution, but at the end of the day, I don't really think. Like I think moving forward with backtracking, and then it's like dynamic programming and graphs, I feel like recursion is just something I need to get familiar with. So I want to make sure I understand the solutions so that I can replicate those solutions down the line. I think it just makes more sense to me. Like, okay. Like, if I know that we need 2 different lists, right? And basically the idea here with this question is that like we need to have every sort of combination of numbers. And you can have like let's say we start off with 1, right? Or if we have an empty list, we can add one, we could choose to add 1 or not add 1, right? And then we can choose to, like if we're at 1, we have a list with 1 in it, we could choose to add 2 or not add 2, right? And then that's basically like the idea that you keep going down, building that tree of making decisions. And it's like the way they even do it is like, I don't know, it's just not intuitive to me. If DFS. I think I just need to watch like a video of someone going through the code, like step by step, line by line, and just tracking like each recursive call. Because right now they do like if the length of no, if if I is greater or equal to, I think you don't even need it for it to be greater. I don't think I will be greater. Let's do this. Nums, right? Res. And you have to append like a copy. I'm just like, what do we do? I'm pretty sure we just what do I need to do? I feel like we're gonna need to at some point we're gonna need to pop, I think, from the subset list and then call the recursive function again. Like, I don't know. So we're gonna append. See, I just need to, I need to watch a video. Sometimes I think watching a YouTube video, like just reading an article of someone solving a problem makes more sense than watching a video. Because I don't have to keep like rewinding when they say a sentence I don't understand. Maybe honestly, I think I'm gonna start from just like I'm actually for real. The basics of backtracking is just DFS, where you add something to a set of data, call DFS on it, then when it returns, you remove what you added. before adding the next thing. Three dynamic program. Okay. So I'm gonna use this to, what was the eraser? Anyway. These geometries. I don't know. I think I'm gonna just keep going through and going over solutions. I think there's no point in spending too much time on it. I think maybe I just need to keep doing the problem multiple times.
Hey everyone, today we are going to solve the Leetcode question subsets. Okay, so let me explain with this example 1, 2, 3. So to create a subset, we have two choices for each number. So one is include current number, and the other choice is not include current number. So I will create a tree so that you can understand easily. So first of all, we have two choices. So first number is 1. So if we include 1, so we create like a 1, right? And if we don't include 1, so we will create an empty list, right? And then, so let's go to left side. So next, we have 2. So we have two choice, include 2 or not include 2. So if we include 2, list should be 1, 2.
Okay, get that.
If not, so still 1, right? And then move next, we have 3. So we have two choice, include 3 or not include 3. And then let's go to left side. So if we include 3, so we will create 1, 2, 3. So this is one of the subsets, right? And then if we don't include 3, so we will create.
So I guess
1,
like
2.
I kind of understand
So
in a sense, right? Because so I understand this, right? We're appending, like this is the choice to basically append down the left side. So we're appending down this side. And then we're also going to pop to like go back up here. And then I believe go down this side, right?
Subsets. And then we finish this part. So let's move back until 1. And in this case, so we go to like include case. And let's go to right side. This is not include 2. So that's why we still have only 1. And the next choice is include 3 or not include 3. And if we include 3, so we will create 1, 3. So this is one of subsets. And if we not include 3, so we will create only 1. So this is one of subsets. Then we finish left side. So let's move back until top and go to right. So still empty, right? So this case is not include 1. So let's think about 2. So if we include 2, so we create 2, right? This. And if we not include 2, so still empty, right? And then let's think about include 3. This case or 3, this is to int the input array. So that's why time complexity should be 2 to the power of n. So in this case, n equals 3, right? So that means 2 multiply 2 multiply 2. So that is 8. So this number is n. So let's just delete it and passing the index 0. And then return result variable. So let's create, first of all, create a result variable with empty list and subset with empty list. And let's say create a subset and passing the index 0. And then return result variable. So let's create subset as an inner function. So create subset, and this is index number. So let's say I. So first of all, if I equal length of input array, so in that case, it's time to add current subset to result variable, because this means we finish checking all numbers, like include current number or not include current number. So result dot append and subset. So we need a copy, so, and we can do like this, just colon, and then return. And if not the case, let's think about include case. So subset dot append and current number, so nums dot I. And then we should move next number. So call create subset, and index number should be I plus 1, right? So this is an include case. And we have one more choice, not include case. So that's why, first of all, we should pop current number from subset. So subset dot pop. And then we should move next index number. So that's why create subset and I plus 1. Yeah, so let me submit it. Yeah, looks good. And the time complexity of
Like, bro, I don't know, bro. I think I get it. I think I just need to keep doing more problems. I think that's what it is. So I think in a way I kind of have to just memorize like the basic problems, you know, the fundamental ones. And then just like that will help strengthen my understanding. I'm even appending. Oh no, I am. Hold on. I am appending. Mm. Nums I. Mm. This had been. Should this be I? Did I do less than or equal to? No, if I is greater than or equal to. Oh no, it should be less than. Oh. Oh no, no, this should be greater than. What am I doing? What am I doing, bro? What is? What's the issue here? Oh, I have to return. I just have to return. I forgot. Yeah, let's just do. Let's do another question. How many backtracking are there? 1, 2, 3, 4, 5, 6, 7, 8. Medium. Usually, based on this, if I can figure out something. Given an array of distinct integers, candidates, and a target integer target. Let's see. Given an array, distinct integers, candidates, and a target integer target, return a list of all unique combinations. Where the chosen number is some target. Given an array of distinct integers, candidates, and a target integer target, return a list of all unique combinations of candidates where the chosen number is sum to target. Any number may be chosen from candidates. The frequency of at least one of the chosen numbers is different. Let me see the example. This is my first time seeing the problem, by the way. Okay. Candidates equals 2, 3, 6, 7. Target 7. Oh, okay. So you can use two, so like each number as many times as you want. Yeah. Yep. Okay. So I think let's do the whiteboard right here. So if we have like for this example, right, candidates equals 2, 3, 6, 7. 2, 3, 6, 7. Oh, I feel like drawing with the mouse. So difficult. Ugh. So what can we do? We are going to have I mean, I guess you have to just go through and do like can you use the same method as before? Where you start with like, okay, you have an empty list. And then we go to I don't know, like add to. Right? And then can it be like this would be not adding to, and this can be like I guess the thing that is difficult for me to understand is you can use each number as many times as you want. So you can't just like go through the array and kind of do what we did last time, right? Like we can have 2, 3, and then this one is still going to just be 2. But there's not really any point in going down this way, is there? Like, what if it was 2? We go on the left side 2. Look at a hint. Is there a hint? Look at the discussion. How do I like move? Yeah, but I don't know. Let's maybe we do like start with an empty list. 2. Maybe actually instead of just like adding numbers, I think we should be adding the, like we should be making the decision based on like summing numbers. You know what I mean? So like we can add 2. Right? And I think like maybe like the left side is adding your like another number, like adding itself. You can add itself, right? So you have like 2, 2. Right now you have 4. And then this can be adding a different number. So we have 2, 3. Right? Because I don't think, what is the other option like? I guess we could add like no number, right? But in this case, this is just going to be checking if sum equals like target. Right? So we have like this branch, we add the same number. Like we'll add the, here, this one will add a new number, 3. But then we'll have like 2, 2. I have 2, 3. Then what? 2, 3, 6. It's a possibility here. I don't know. Watch a YouTube video. Gosh. Anytime I see like a solution where the time is like over 10 minutes, it's just like, it just makes me sigh.
The search for your next where to starts here. Whether you travel to feed your inner...
Hey everyone, welcome back, and let's write some more Leetcode today. So today let's solve combination sum, and this is another problem from that blind 75 list. The link will be in the description. So we are doing one more problem and have very few problems from this list remaining. So we're given an array of distinct integers called candidates, and we're given a target integer called target, and we just want to return a list of all the unique combinations of candidates where all those numbers end up summing to the target value. And we're allowed to return those combinations in any order, and we're also allowed to use the same number from candidates multiple times. But we don't want to have duplicate combinations. For example, if 2, 2, 3 sums up to 7, right? That means 3, 2, 2. These are the exact same values, right? Just in a different order. These sum to 7 as well. So we don't want to add both of these combinations to the result because they're the exact same. So what we're saying is we want combinations, we don't want permutations that end up summing to the target value. So in this example, you can see that we are given these candidates and a target of 7, and we have 2 different ways that we can sum up to 7. Of course, 7 by itself does sum up to the target, and 2 occurrences of the 2 value and 1 occurrence of the 3 value added together are going to lead to 7 as well. So then we return these 2 combinations as our result. So I would say the difficult part about this problem is trying to figure out how to eliminate duplicate combinations, right? For example, if we just brute force it like a decision tree, so we have 4 different values we can choose each of them an unlimited number of times. What we can do is have 4 decisions in our decision tree, right? Like that might be the naive thing that you start with. So we would get 2, 3, 6, and 7, and then we'd basically continue that, right? On one path over here, we would find, okay, we found the 7, so we found the target, right? So we found one way that we can reach the target. So therefore, we don't need to continue down here because as we add more numbers, all of these values are going to be positive. So as we add more numbers, we're only going to get a sum larger than the target. So, you know, I think it's kind of obvious why we don't continue down this path, right? But down here from the 6, let's try to continue, right? We can add a 2, so we'd get 6, 2. We could add a 3, so we'd get a 6, 3. We could add another 6, so we'd get 6, 6. And we could add a 7, where we'd get 6, 7. So notice how all of these are going to sum to a value greater than the target. So down this path, we never ended up reaching the target. We only went over the target. So we don't continue down any of these paths, right? But now let's continue down this path. So here we can get another 2. We can get a 3. We could get a 2, 6, but in that case we would get 8, which goes over our target. We could also get a 7, 2, 7, but that also goes over our target. Now here's the part where we're going to end up getting duplicates. So I'm going to show you why this type of decision tree does not work. So here we could get a 3, for example, right? So we'd get 2, 2, 3. Now that sums to the target. Down this path we could choose a 2, so we'd get 2, 3, 2. Notice how both of these end up summing to 7, but they're the exact same. They're just in a different order. We have 2 2s and a 3. Here we also have 2 2s and a 3. So we ended up getting the same one twice. So this works in finding the combinations, but we end up getting duplicate combinations. So what kind of decision tree can we try that gets us the result that we want, but does not have these duplicates? Let me show you how we're going to do that. Let's logically think about this. We know that we have one value in our candidates, 2, right? So we can try to get all combinations that include this 2 value, right? And see if any of those combinations leads us to the target value 7. Now, we could also... So then if we make a second decision over here, right, in this decision, we're definitely including at least 1, 2. Now, if we go down this path, we want to make sure that none of the combinations down this path ever match the combinations down this path. How can we guarantee that? Well, in this side, we said we're definitely including at least 1, 2. How about in this side, we don't include even a single 2? So basically, we skip 2. So here we're going to have an empty array because we skipped the 2, right? All we said is we were able to start from here, but we said no, we're just not including a 2. We're just going to do combinations with these 3 values. That's going to guarantee that none of the combinations on both sides are going to be matching. And that's basically the logic that we're going to follow. So from here, remember, we can include multiple 2s if we want to, right? So one decision here could be including a second 2. So we get 2, 2. Now, this path is going to include all combinations that include at least 2 2s, right? But remember, our definition for this decision tree needs to be recursive, right? Because we don't want any of the combinations down this path to be the same as any of the combinations down this path. So what we said here is we're going to include 2 2s. How about down this path? We say that we're not including any more 2s now. What we're saying is we had 1 2, but now we're done. We're skipping 2s. Now we're only going to use values from here. So that's the recursive thing, right? We're basically basically doing the same decision down here as we did up
Added
here.
their number.
So here we're going to say we ended up skipping the 2, and we still only have one single 2. And so let's just continue to repeat that. So over here, we're going to add another 2. So we'll have 2, 2, 2. And over here, we'll say, okay, now we're done with 2s, right? Where we're going to keep ourselves at a limit of 2 occurrences of 2. And we're basically going to continue this logic until we get to our base case. So over here, you're going to see if we ended up having 4 2s, we'll get a target of 8. So therefore, we went over our target value. So we're going to stop. But down here, right, this was our path where we said, okay, we're not going to include any more 2s in this path. So here we can make a decision. We can add a 3. So then we'd get 2, 2, 3. So we're continuing that recursive definition. And so notice how we have 2, 2, 3, that's 7, so we did find at least one combination. But remember down now, if we make a decision to the right, we want to make sure we don't have any duplicates from here. So in this side, we decided to add 1, 3. How about down this path, we say we're done adding 3s. We're not even going to add a single extra 3. So this is going to remain as 2, 2. Now, I think it's pretty obvious that down here, since we're only allowed to add values 6 and 7, neither of these is going to end up leading to the target. If we add a 6, we'll get a total of 10. If we add a 7, we'll get a total of 11. Neither of these, both of these go over our target. So let's quickly run through the rest of the decision tree. So over here we said we added a second 2. So over here, we're not going to be adding any more 2s. So here we can add a 3. So we'd get 2, 3. And over here, we would skip adding 3s, right? So we're not going to add any more 3s. This is going to remain as 2. Now down this path, at this point we have a total of 5, so we're only allowed to add values 3, 6, or 7. All of those are going to end up leading to a total of greater than 7, so we won't be able to find any solutions down this path. I'm just skipping drawing it out because we're kind of running out of room. Now over here, what we said is we skipped 2, and since this path includes the one where we added a 3, so here we're not going to add any 3s, and so we're only allowed to choose 6 and 7. That's going to end up leading to totals of greater than, it's going to lead to either 8 or 9. Those are both greater than our target value. So here, we're not allowed to add any 2s because that's what this path was, so we can add a 3, or we can choose to skip 3 and add nothing. So here, since we're skipping 3, so we're only allowed to add 6s or 7. So here we can say, okay, get a 6. This path, we skip 6, so we're not allowed to add any 6s over here. And from over here, we'll say, okay, we can add a 7, which will give us the total 7, right? That's the target that we're looking for. So we did end up finding that. So that's our second solution that we found. Now, since this path is going to lead to combinations that do include a 7, this path cannot include a 7, but you notice how as we are continuing to go down right paths, what we're saying is, okay, we're basically removing the number of elements we can choose from, right? We're popping 2 initially over here. Then when we go down here, we're not allowing ourselves to choose 3. Over here, we can't choose 6. Then when we finally go down all the way over here, we're not even allowed to choose 7. So therefore, we have no choices left. So this is also going to be a base case because we ran out of elements. And the way we're going to be tracking which elements we can choose from is we're going to have a pointer. Let's call it I. And so initially it's going to be here, which means we can choose any of these elements. As we pop an element like this one, we'd end up taking our I pointer and shifting it over here, which tells us, okay, we can only choose these elements now. So that's the main idea. This is going to be a recursion tree. Each recursion step, we can make 2 decisions, and it's pretty easy to code up once you can kind of understand this logic. Let me show you how to do that. By the way, the time complexity of this, you can see that our decision tree, we're making 2 decisions each time. So it's going to be 2 to the power.
Let me try coding something up. Candidates. Well, actually, I mean, if I think you just want to return. I don't think you want to do anything. If what else do you want to do? I want to. We want to append. We want to append. I don't think we're gonna. Are we gonna increment to the next one? I don't think so. Oh my god, I did nums, but I meant candidates. Damn. Recycle this one.
what's the height of our decision tree going to be? Well, each value in this is going to be positive. It's going to be at least 1. So the height of the decision tree can be at most whatever the target value we're trying to make it. So 2 to the power of t, where t is the target value. That's going to be the big O and big O time complexity of this problem. So we are going to do this recursively, but let's have our result variable, which is basically going to be global for the scope of this problem, because I'm going to define a depth first search function inside of our outer function. So a few variables we're going to pass into here. We do want to maintain which of the candidates we're still allowed to choose. So like I said, we're going to have a pointer I that's going to determine that. We're also going to have a current variable. We're only going to have a single occurrence of this. It's just going to be a list that tells us what values we have added so far to the current combination. For example, like we could have 2, we could have 2, 2, right? 2, 2, 3, etc., etc. And for the values in our current combination, we do want to have a total. So we want to be maintaining what's the total sum of those, because if it ever reaches our target sum, then we know we have found a solution. If we ever go over our target sum, that means we've reached the base case and we can't continue anymore. So in our DFS function, let's go ahead and define those base cases. We know the base case is if total ever ends up reaching target, that means we found the result. So what we're going to do is result.append. We want to append the actual combination, so we're going to append current. And since we're only maintaining a single variable list for current, we don't want to actually append current itself. We want to create a copy of it, because we're going to continue to use this current variable when we're doing the other combinations recursively. So we don't, because then we're going to be modifying it. So we just want.
Yeah, I should do that.
To create a single copy before we actually add it to the result. And after we're done with that, we don't want to continue the rest of this function, so we're just going to go ahead and break out of it by returning. So that's the base case where we succeed. What's the base cases if we end up being impossible to find a combination? Well, one is going to be if I is out of bounds, meaning we can't choose any more candidates. So if I is greater than or equal to candidates, or our total ended up going over the target that we're trying to reach. That's a base case where we have to return immediately because we cannot find.
Is that no? I did that. So okay, my thought process is there. The sum is greater than the target. Yeah.
A combination then. Now for the actual recursive step. Remember, we have 2 decisions to make. We can choose to include the value at candidates of I, right? We can choose to include this value. So what are we going to do if we're including this value? Well, first of all, we're going to take our current values that are in our combination. We're going to take that candidate and go ahead and append it to our current combination, right?
Okay, yeah. So
we're going to do that before we end up actually calling our DFS function. So we're going to call DFS. And what are we going to pass in? Well, we're including this candidate so we can potentially continue to include it, right? So what we're going to say for our index I that we're passing in is I stays the same, right? We're not restricting which candidates we're allowed to choose from just yet.
Okay.
So I stays the same. We pass in current because we just updated it right now, so we can go ahead and pass it in. And the total did end up changing, so we took our current total and added this candidate to it, right? So we can go ahead and pass in total plus candidates of I. So let me delete this line because we're not doing anything with it. But yeah, so this is going to be that first decision where we do include the candidate. Now the next decision is going to be where we can't include it. But after we called this function, we want to clean up a little bit. We ended up adding this value to our current candidates, our current combination. So we want to go ahead and pop that before we go down the other decision. And so once we've popped that, we can go down the other decision. That's if we're not ever going to include this candidate. So for the index, we're going to pass in I plus 1, indicating that we can't include any occurrences of I. And for current, we can just go ahead and pass in our current combination. And total is going to stay the same because we didn't end up adding any value to it, right? We left our current combination as the same as it was before when we actually called this function. And once that's done, we've basically made our 2 decisions, right? Can you see what's going on? Can you see that we called depth first search once and then we called it a second time? So we did create that 2 branch decision. And after we're done with that, we can go ahead and return. And in this case, we actually don't need to return. So that is the entire DFS function. Last but not least, what we want to do is actually call it out here. So we're going to call it, passing in 0 as the beginning index, passing in an empty array as the current combination, and passing in 0 as the current total. And then once that is done, we will have updated our result, which we declared up here, and then we can simply go ahead and return that result. It should contain all of the combinations that end up totaling to the target. So you can see this problem isn't too bad to code. This backtracking approach isn't too bad.
No, it's not. That's actually not that bad. It made sense. Because at first I had... Yo! Are you serious? So you're telling me my issue was that I passed in I here, and that's why I was getting recursive. Bro, okay. Yeah, we're here. Bro. Yo, don't let this submit. This submit, bro. Listen. Yo, so my logic was here, bro. My logic was here. You know, I need to work on the implementation, but the logic is here, bro. Don't get it twisted. I'm seeing patterns. I think that's my dad's phone. I don't know. I'm probably gonna stop here. I have to. Oh, I have other work to do, bro. It's already 4. I want to take a break and then finish, but no, I'm gonna end on the high note, bro. This was good. I need to start revisiting other sections too. I might start revisiting other sections once I do graphs. Once I do graphs, then I'm probably gonna just work on like revisiting all the other sections. I'm gonna do dynamic programming, but it's like, am I gonna focus on it really? Like how much? Like how often are these questions asked at companies that aren't like Fang? Do they really be asking dynamic programming? It makes it go for memoization. The thing I hate with like missing days is when it's like I was going in May, bro. Look at this shit. I'm going crazy. 92 problems solved. I'm going to stop here though. Okay. I'll be back tomorrow. I'm not doing anything tomorrow, so I'll be back. I'm not really going to be doing anything pretty much the whole week. So yeah. I'll probably be streaming most days. I'm trying to be more consistent about it. Even though my goal really is just to stream like twice a week. I think streaming every time I Leetcode sometimes is not my favorite thing. Because sometimes I really just want to like honestly I just want to watch like a YouTube video or something while I'm doing work. But I can't. I get kind of afraid of copyright and stuff. Anyway. Yeah.